Okay. Welcome back, everyone. Hope you all had an interesting coffee break. It is my pleasure to welcome Professor Alok Laddha from the Chennai Mathematical Institute. Alok is widely recognized for his contributions to our understanding of the infrared structure of gauge theories and gravity. His work has helped deepen our understanding of the subtle connections between soft theorems, asymptotic symmetries, and memory effects, revealing how these seemingly unrelated phenomena could originate from a common infrared framework. During these lectures, Alok will tell us about tail effects in gravitational radiation, how they help us understand better gravitational memory, as well as the infrared structure of gravity. So please join me in giving a warm welcome to Professor Alok.
Thank you. So I should start by saying, unfortunately for me, I'm not Ashok Sen. So you have to tolerate my lectures, first two lectures, and then real Ashok Sen will come in lecture. So let me start by giving a basic introduction of what Ashok was planning to do. Hopefully I will stay faithful to what he had planned. So we write the title of this, at least the first two lectures. Can you see the writing? Bigger, okay. Okay, so let me start by giving you a basic idea of what the soft theorems are. And at any point you have any questions, because I know audience would have wide background, so please stop me at any point. So let's start with a very simple example. Let us say that we have two black holes, let's say of mass m1 with some initial momentum p1, m2 and p2. And right now I'm depicting these black holes as point particle as Jan explained, but we will be more precise about what exactly this means to say that a Schwarzschild black hole is a point particle. And let us say that they scatter, and there could be a very complicated theory of gravity. It may not even be Einstein's theory. It can be Einstein's theory plus corrections, etc. And many things could happen. I mean, depending on how close they are or far they are, they could scatter into two black holes with some momenta p3 and p4, or they could even merge. Another scenario is they could even merge and give you a single black hole with some mass m and some momentum. For example, less than p1 plus p2, because some of it could be radiated in the gravitational. So several scenarios happen depending on what happens in the scattering, how these things scatter. And of course, because any theory of gravity, let's say Einstein's theory, as you know, it's highly nonlinear. And if you want to compute how much radiation is emitted in this process, so you want to look at gravitational radiation at large distance from, let's say, where the dominant scattering was happening, then that gravitational radiation, if you want to compute as a function of t and x, so you have a detector which is sitting at a large distance x, and you want to it was switched on at some time t, and you want to compute how much radiation came. So, but to compute it from equations of motion, as you know, is very complicated, analytically not possible. So this is analytically impossible. And of course, it will depend on the details of the scattering also. I mean, what happens, what is the theory, what is the structure of the stars or black holes, and how far or close they are during the scattering process. So usually what people do, and I think maybe Jan also covered this a little bit, is that people have approximation techniques. And two of the most common techniques that I think most of you would be familiar with. One is what is called post-Newtonian expansion, which is basically the statement that if you have two black holes which start with very low velocities and they stay far apart, so they never accelerate too much, then you could compute the radiation in expansion in V by C. So this is an expansion in I'm being schematic here, but you understand what I'm saying in V by C, assuming that they never accelerate too much and the velocities, if they start with small velocities, it would remain small. But it could happen that it could even happen that you have two black holes which came with high relativistic velocity, black holes or stars, and but the distance between the impact parameter of the scattering is much larger than the Schwarzschild radius. So we cannot apply post-Newtonian approximation if the velocities are high. But there's another technique which is called post-Minkowskian expansion. And this is an expansion in G. So if the black holes remain far apart, then the gravitational field between them is very weak. And so you can do perturbation theory in small weak gravity approximation, and that is the expansion in G. Is this clear? So, and many of you may be familiar with in-spiral. In the in-spiral case, of course, these two are related because of the equation of motion for the in-spiral, the centripetal force equation. But in the case of a scattering, it's not, they are just independent approximation schemes. So you could have one without the other. But these are the most common, approximation technique. However, there is one which is is going to be the focus of this lecture, and that's a different expansion technique. So in both of these cases, you see that you are doing expansion in the parameters intrinsic to the system. So you're doing expansion in the velocity of the particles which are scattering, and here you're doing expansion in the weak field approximation, basically depending on the impact parameter of the scattering. But there is an expansion scheme which is in terms of the frequency of the detector. So that's an expansion scheme which we will call soft expansion, and this is what we will spend a lot of time understanding. And this expansion scheme is as follows. So let us say that let the characteristic frequency of the scattering. So let us say that there is some characteristic frequency of the scattering depending on how the impact parameter or the mass of the black hole if they are merging of scattering the F. And let us say that, of course, a detector is in our hand, right? So we can say that the detector is switched on in a window. So let us say that a detector, which is detecting the radiation, switches on between some frequency omega and omega plus delta omega. So it has some resolution, the detector, but it's only switched on around frequency omega. Now, if omega by f is small parameter, then as you will see that we can obtain some very striking analytical results for the gravitational radiation that the detector measures. So in this case, then even without PM or PN approximation, we can obtain exact results. And by exact results, I mean the results which do not depend on what happened in this blob region. They would be insensitive to what happens in the blob region. That would depend on what are the momenta, mass of the black holes, etc., but not on any details of the scattering. So that's why they are exact. They are not results which depend on a case-by-case analysis of your scattering. And these exact results are what are called soft theorems, or classical soft theorems. In gravity. So I will stop here and see if there is any question, at least about the setup of what the soft expansion is. Oh, sorry. Where is the here? Yeah, if this parameter omega is the frequency of detector, and if this is less than 1, then even without any PM or PN approximation, we can obtain exact result for computing the radiation. F is the characteristic frequency of the scattering. So one example would be inverse of impact parameter. Right? So that's the dimensionless parameter in which we will do the expansion. So here the dimensionless parameter is V by C. Here the dimensionless parameter will be whatever that you could obtain using in a weak field approximation. And here it is really the frequency of the detector that you are expanding around. Okay, so let me first write down what these results are, and then we will spend first 2 lectures in covering part of this, how to derive these results. So, let us start with. So let's first start with the setup. So setup is the following. Assume, and this assumption is a big assumption, and Ashok will repair this assumption in the lectures that he comes in. So assume that at t equal to minus infinity, so in the far past, we have m incoming objects. And I will be more precise about what I mean by these objects. But for now, just think of them as point particle with multiple moments. Okay, so we will connect them more precisely with why we can treat like a Schwarzschild black hole as a point particle, something Jan also touched upon. But for now, if you don't want to think of it as a black hole, just think of it as a point particle which can have other data like spin and multiple movements. So m incoming objects with mass mi, momentum pi. It can also have a so this is pi mu. It can have a spin like intrinsic spin, which is sigma mu nu. It can also have some other multiple moments where I goes from 1 to m. So the setup is that at t equal to minus infinity, you have m incoming objects which are coming from far apart, and then they're scattering. And at t equal to plus infinity, they scatter into n outgoing objects. So you may worry why I'm not taking m equal to n if it's classical scattering, there is no particle production, but we are allowing for merger. So, we are allowing for merger, we are allowing for supernova explosion. So, the number of objects is not conserved, even though it's nothing quantum here, into n outgoing objects with the data m prime. So prime will be always for the outgoing. Okay, so this is our setup. We are saying that, let me draw it so that it becomes a little more clear. So this is my Minkowski space-time. Of course, the space-time actually is not Minkowski because we have gravity. But what we are saying is that at t equal to minus infinity, objects come from far apart. So your objects come in from t equal to minus infinity, and then they do things that we are not in control of. We have no idea. They could do anything. And then they scatter into n outgoing objects. And of course, there will be a lot of radiation that will come out. And this radiation will be detected at infinity. Of course, I'm drawing it like this because it travels in direction of light, 45 degrees. So there is some detector we are placing. And it's going to detect this radiation. So this is our setup. And so now the statement is that, so in the past, since here, these objects are far apart, and here they are far apart, you can imagine that the space-time in far past and far future is almost flat. And of course, even if you go very far away from where the dominant scattering is happening, like merger is happening, where the detector is placed, as most of you would know, detector is always kept very far away from the source. And so even in this region, space-time is approximately flat. which means that we can expand this space metric, which is solution to our equations of motion with this source as now, we are not assuming that h mu nu is small everywhere. Is this clear? But what we are assuming is that where we are detecting radiation, which is at a very far distance, the metric is eta plus h. Is this part clear? And so if you take this h mu nu x, let me write it more explicitly, x0 mod x, and the angle, which we will call x hat, then we are interested in radiation. So we are interested in the case where mod x is very, very large. Now large compared to what? Let us assume that we fix origin of our space-time somewhere in the middle of the scattering. So this it doesn't matter where it is, it's just somewhere where the scattering is taking place. So there is some origin we choose. And then we are measuring spatial distance with respect to that origin. And then, you can, this is something we will see. So I'm going to write a result and then we will expand on it. You can see that because we are interested in this expansion parameter. So our detector is, sharply peaked around some frequency. This is something that is in a time domain. So of course, if you want to go to frequency domain, as you all know, what we have to do is to do a Fourier transform. And then we can call it as, with the usual convention for Fourier transform. So this is the gravitational field at any distance x. Right now, I'm not even taking so far large in frequency domain, but we are interested in large x expansion. And so as we will see that this expansion has the following form. This is something we will derive. So I'm just writing the expansion. So it's of the form, let me put it as a 0. Where d is the dimension of spacetime. And these dots mean terms which are higher order in 1 by mod x. So if you are in 4 dimension, then this will go as 1 by x squared terms or higher order terms. So one of the things that you may have also studied from Jackson when you study radiation is that the radiative field in electromagnetism, and it's same in gravity, is falls off at this power. So in 4 dimension, it will be familiar to you because this is 1 by x, and that's how the radiation field falls off. So, the first thing is without any soft expansion, anything, this is just a fact of life, that if you want to study radiation, then you have to focus on this, component of the expansion. And now the statements we are making are the statement about this component. So this component is what is typically called radiative field, because that's what the detector detects. Well, as you can see, it depends on omega and the direction at which you are measuring where your detector is placed. Yes. D minus 2 by 2. So, the whole thing by 2. We will see this, why this comes, but you may be wondering why I'm doing D dimension, because of course, the only case of relevance here is D equal to 4. But as we will see that it is much easier to understand the structures when we first assume D is larger than 4 and then go to D equal to 4. So somehow, for understanding these results, it's better to first work with D larger than 4 because many things become simpler. Okay, so that's the statement, and now I will write soft. Is there this is the, okay. So now I will write so this is the radiative field, and all the statements we are making is about computation of this radiative field. So of course, even if you do this post-Newtonian or post-Minkowskian expansion, your goal is to compute this for a scattering. And so now I will write the classical soft theorem. which is a result, analytic result about this particular object. And I want you to remember always that till I say otherwise, we are assuming that in the past and the future, all the objects are moving freely, because they're far away from each other. And this is a crucial assumption for what I'm going to write now. And then, Ashok will tell you how to repair this. There is something that goes off with this assumption in 4 dimension, and Ashok will tell you how to repair it. So this is the statement of soft theorem, that this object, actually I should be a little more precise, so let me write here. And there is some normalization, n, which depends on omega, which I'm right now suppressing. Okay, it's not. Let me take all the omega where we want. So n, which depends on factors of pi, basically nothing else. And so there is a phase, overall phase here. And remember, mod x is the distance of detector from the center of scattering. So I am just writing that object, and that object has the following form. So my incoming objects were M. Also, I will be little cavalier about raising, lowering indices, because we are at large distance, whereas we saw the spacetime is almost Minkowskian. So these indices are raised and lowered with respect to eta, okay, not any g. So that's why I'm with, yeah. And I will explain this notation, what I'm writing here. Oh, M, sorry. If something is not clear, visible, please ask me. Okay, now I'll explain the notations, all the notation that I've introduced. This one, of course, we already have. That's the frequency of the detector. Pi is the moment of the incoming objects. And this x hat is really a null vector that is defined by the direction. So this x hat is, of course, theta phi. And this x hat is really, because this is a four vector dot product. So this x hat mu is simply 1 and x hat. I hope this notation is clear. So I'm sorry, I'm using the same x hat, but whenever we use it as in part of a dot product, always remember that it is just the null vector that we define using the angle. So that's the direction in the sky, and that always gives us a null vector. And this another object we have so far not defined is J, and this Ji mu rho is the where Li mu rho is suitably defined orbital angular moment. And we will see how to exactly define it. Because we have chosen some origin, so there is each object which is scattering as an orbital angular momentum, and that we are indicating as Li. And there is if the objects have spin, this thing here, then the net angular momentum is what we call J, like in quantum mechanics, and that I just write it like this. And so this is the next term. And now you can notice that why I wrote it like this, because this is 1 by omega. So it is very, in small omega, it's a dominant term. And this term, as you can notice, is, oh, I did not tell you what K is. Sorry about that. So K mu is this is K mu. So now you notice that here it's one, this term is 1 by omega, but this term is, you have k in numerator and denominator, so this is of the order omega to the 0. So this is clearly subleading compared to this term. Is this clear? In the small omega expansion. Oh, I cannot cross. And of course, if you're doing small omega expansion, you have higher order terms, which let me just write right now as order omega. And the one immediate result that we will prove is that the assuming particles or objects are free, these two terms for the radiation are universal. They don't depend on the details of the scattering. They don't even depend if the theory is GR or GR plus higher order corrections. So the only thing that depend on is some information about, not even the complete information, but the objects in the far past and the far future. Is this part clear? Yes. Yeah, P prime, what did I? Oh, yeah, this one, yeah. Yeah, it's, oh, you mean it should be J. Thank you. Yes. No, K is same because K is the, K is just the, K is just depends on the frequency of the detector and the direction in which you're placing the detector. So that doesn't depend on incoming or outgoing. N. Yeah, outgoing number is N. So it's just some are all outgoing objects. These some are all incoming. Is the same like this. Incoming sum, outgoing sum here also, except that this term is subleading in the small omega expansion, and it depends on, whereas these things only depend on the linear moment of your objects. This one depends on the linear momentum as well as the angular momentum of the objects. And so these two results are completely universal with that crucial assumption, and that's why they are called classical soft theorems. Or let me put it, I'll put it like this because it's under that assumption that objects are free in the far future and far. So classical soft. And this one is called leading. This term is called the leading soft theorem. I mean, because it's leading in the soft expansion. And this one is then unimaginatively called subleading soft theorem. Okay, so, yeah. Oh, thank you. Yeah. Yes. You will not see any such errors after lecture 2. So you have to bear with me till lecture 2. Yeah, we will exactly come to that. So that's an excellent question. So one of the things is to understand how you get this result and what it means physically. So since you're asking, let me little bit say what physics of this result is, but something we discuss maybe not today, then in the next lecture a lot. So maybe I go here. Yeah. Oh, that's just some normalization. Yeah. I mean, actually you are right. I mean, it was useless because I didn't write this normalization, so it didn't matter. But it's just a habit. Yeah. So let me now say something about the physical interpretation of this. So you notice that first of all, how do we isolate this term, right? This particular term. Let's say that we have an expansion, right? So this 1 by omega, this omega to the 0, and then you have this entire series. But if you want to isolate, let's say this contribution, how will you isolate it? So you will say that one obvious way is to consider take as soft frequency as you can, the detector frequency as low as you can, and you compute this object. Now you can obviously see what happens. If you do this, then this one omega multiplied with 1 by omega cancel, and you get this residue. But every other term will cancel as you go to 0, right? Because so if you do this, then you get the stuff that I have written, the leading soft fact. Let me just call it leading soft fact. But why? What is the physical interpretation of this object. So think about what this object is in the time domain. So in the time domain, this object is nothing but we can write it as limit omega going to 0, e to the I omega t, dou t h mu nu. Right? That's just the way to rewrite it up to some sign. And now if you take omega to 0, this thing drops out. So this becomes 0 at t equal to plus infinity minus t equal to minus infinity. So what is this measuring? This is measuring the net change in your radiation from the far past to the far future. So if you only have wave, if you only have a gravitational wave, then over infinite time they will average to 0. You will never get any difference. So this difference is the it's the static component, because it's zero frequency component, right? Static component of radiation, and it is also called the memory effect. Because it's the static component, so it even if you go to infinitely late time, the memory of radiation has not completely gone away. It has survived. In fact, I have cheated a little bit, because this term that I have written is really what is actually called only linear memory. And this term is, so in the post-Newtonian literature, or even actually post-Minkowskian literature, this term is called spin memory. It's called spin memory because it depends on the spin of the scattering objects. But you can also notice that here I have so far, if here the contribution to this radiation is only coming from the objects which you are scattering. But this cannot be totally true, right? Because of the fact that the gravitational waves themselves can source gravitational radiation, right? Because gravity is not like electromagnetism, so it's a source of itself. So that means that there must be some contribution to this coming from the finite energy gravitational waves itself. And that stuff is called nonlinear memory. So I will write down that full object now. And that is really the final universal statement in full GR. So if you want, this is this is this is a contribution which is assuming that you don't take gravitational back reaction into account. But if you do, then the same formula really, the formula doesn't change structurally. It just gets more terms. So I will write it schematically first. Then we will discuss the more details. So all you have to do is to include is equal to, so I will write all the terms we have written. I will just do it like dot 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 plus and we right now write schematically, because when we derive it we get exact formula. Integral over so this formula you notice is that by P grav you mean the gravitational momentum, linear momentum. So when you integrate over all time, it gives you the net gravitational momentum. Is this clear what I have written? So if you integrate this object over all times, that gives you the total linear momentum flux of the gravitational waves. So that is basically P of the gravitational wave itself. And this object is basically P of the gravitational wave itself, P mu divided by P dot y hat, where y hat is this, x hat. This is y hat is here. So this is really same as this object, except that instead of sum, we have an integral, because gravitational waves are not discrete. Is this part clear? So if you take full back reaction, everything to account, even then the low frequency gravitational radiation has a universal structure, which is given by this term, which is sourced by the objects, the initial and final configuration of the objects, and the net gravitational linear momentum, which is this term. So this is this contributes to this one, and there is a similar contribution here. I will not write it, it's exactly the same. You replace this sum with an integral, replace J with the angular momentum flux of gravity and P with the linear momentum flux of gravity. Okay, so that's the full, is this clear? Yes, D minus 2, thank you so much, yeah. Yes, because we are in D dimensions right now, yes. Yes, so this object is called nonlinear memory. Yeah, that's, yes, exactly. Nonlinear memory. Okay, but for the purpose of these lectures, always think that when I write it like this, it includes gravitational, the nonlinear memory, because only thing we have to worry about is that in the end, this sum should go to integral. Is this clear what I'm saying? Yes. It's for the gravitational wave itself. So the linear momentum flux of the gravitational wave. Yeah. So it's strictly speaking, the flux is itself when you integrate. I'm just writing it like this. So you integrate it, that's the total flux, because you integrate all time. That's the total linear momentum flux of the gravitational wave. Yes. Gravity, just to distinguish. But I mean, my only intention to write this was to convince you that this is really effectively the same form, except in this sum you have to somehow replace with some integral. That's because it's continuous distribution. Yes. Yeah, it's an addition. So this is linear. The whole formula is this plus that. It's same order. It's one by me. So it's, yeah, it's. Yeah, sorry. Yeah, this is the old guy. This is the new guy. Yeah. So that's what we will now discuss, how to prove it. So I'm just telling you the result, and then we see how these two results we derive from general covariance, and that's it. And the assumptions we have made, which is the objects are free in the far past and the far. Say the last line again. No, it's the same. It's exactly the same, except this sum you have some integral. So actually you could think of it being here, except that in the outgoing thing, I will write n plus extra, where extra is the gravitational contribution of the gravitational linear momentum. So you can just think of it like that also. Yeah. No, P grav doesn't, because you integrate all time. I mean, the linear momentum flux. So omega is the frequency of detector. P grav is the momentum, linear momentum of the gravitational emitted gravitational wave. Okay. So now we discuss them. At least we discuss how to. I'll sketch the proof for this. For these two results. How much time? 45 minutes. Yeah. They can also be massless, and excellent point. So they can be massless, and that's why I'm saying we could also think of gravitational momentum as some massless particles which are contributing to this. There will be more contribution, but in general, they are not along. X hat is the direction of the detector, right? So you are right that the closer they become to X hat, you get more contribution from those particles. But in general, these are just arbitrary. null. They're arbitrary null vectors. Yeah, that's an excellent point. So you have to, you are right. I mean, if you choose your specific detector, which is pointing along direction of one of the particles, you get maximum contribution from that particle. Okay, so now I will some proof of the theorem. So again, just only thing is that assumption, and for simplicity, I will assume that. So this is not assumption. This is just because Blackboard has limited space. So that's the only thing. For this lecture, we assume that that all sigma I mu nu equal to 0, and sigma I prime. So we are not assuming that there are no higher multiple moments, but we are assuming that there is no spin. This what we call spin angular momentum for this object. This is only for simplicity. I mean, I will give you references where you can see how it can be generalized, but no new conceptual thing comes. That's why I'm avoiding the. Of course, it doesn't mean J is 0 because J still has a contribution from the orbital angular momentum. So it's not like this term will go away. It's just it'll be simpler to prove this this result. Okay. But let me, before proceeding, let me give a brief sketch of why we say, and I think Jan also indicated this, why we say that we can treat black holes as like Schwarzschild occur black hole as point particles or neutron star as point particles. And it's obviously one idea is intuitive that if you go over large distance, a star or a black hole would look like a point particle because its detailed structure is not visible if you look at it from large distance. It's exactly like electromagnetism, right? That if you have a charge distribution, then very large distance it's monopole. Then if you go a little further, it's dipole, etc. But it's still interesting to see how we can. I mean, if you are a believer in Weinberg's book on gravitational cosmology, this statement is obvious. But if you are a believer in Wald, then you may want to throw some book at me. So it's maybe important to also see quantitatively how this can be, because it's a nice little derivation. So let me first. So before doing the proof, one claim. And what is absolutely remarkable is what I will say, explain for Schwarzschild, how to treat Schwarzschild as a point particle. The statement is also true for Kerr black hole, but that I will just write the final result. So claim is that we can model Schwarzschild black hole. Let's say it is moving in influence of some force, so it has some velocity moving. Okay, so model a Schwarzschild black hole as a point particle with the stress tensor. So is this notation clear? So sigma is some proper time of the particle. So we are integrating along the trajectory, and this is just usual stress tensor of a point particle. Is this formula familiar to all of you? Nothing to do with black hole, just for a point particle. If you have a particle with no other intrinsic structure, then its stress tensor can be written like this at any point x in space-time. So of course it is localized on the trajectory of the particle. There's nowhere else it has any contribution. Now what this object has to do with Schwarzschild, that's what we want to understand. So because we are saying Schwarzschild can be understood as a point particle, right? So let me argue what the connection is. And the reason I'm saying it is because this connection is also true for Kerr black hole. And actually that has several potentially deep ramifications also. So let's first do Schwarzschild. So If I get anything wrong, Jan will correct me because he's he's one of the experts in this. So first statement is that the Schwarzschild metric, exact Schwarzschild metric, can be written in this form. I will tell you why in a minute. Where L mu is some covector which we can write as. So I will explain what these notations are in a minute. Where U is like a 4 velocity vector. So U mu do mu is just do T, and N is the radial vector. So N mu do mu is do R. So the first claim is that, oh, I forgot the most important part. The first claim is that we can write the Schwarzschild metric in this form, where R is the it's so if this is at a point X, then R is we put Z here. So if you have where Z mu tau, we can take it to be simply U mu tau. So the first statement is that if you have a Schwarzschild black hole moving with some uniform velocity, we can write the metric in this form. Let me tell you why if it's at rest, which is the simplest case. So if it's at rest, then so we do a simplest case, which is the usual Schwarzschild. So if U mu is 1, 0, then clearly R is mod X. Just mod X. And then, okay, so you can ask, so that's the usual radius, so the usual radial coordinate. Then you can ask why this is how this is a usual Schwarzschild metric. If you now write this metric, then this metric has a form, I mean, this I've written in this mu form, but if you write the line element, then it is the usual Minkowski line element. We are always going to work with mostly plus signature. You can just expand and check, okay, this is true. And now you can say that if you do a coordinate transformation, which is, what is it, the T dt is dt Schwarzschild plus 2gm dr by r minus 2gm. So you change from T to T Schwarzschild, then you check that this gives you the usual Schwarzschild metric that you write in the exterior of the horizon. So it's just a coordinate change. Is this clear what we did? So you start with this form, which is like flat plus something, and you can see that the line element is of this form then, and then that can be written as a Schwarzschild by some coordinate transformation. Is this clear what we have done? Okay. Then why am I doing this? Because you can show something quite remarkable, which was shown by Justin Wines in, was it in 2016 or? Yeah. I think it was 2016 or 17. So I will give you the exact reference tomorrow. So this was a beautiful, absolutely beautiful work by Justin Wines. I mean, I'm giving you a very cheap example, Schwarzschild. He did this for curve, which is what his real non-triviality was. So what he realized was the following, that, if you take this guy, then you can write it as I will explain what the exact term is. This is not just algebra, so I'm keeping all the steps. So you can rewrite this as where zeta is some 4 vector, which is given by so of course, recall that this is a partial effect of the flat metric. So this is not just a ordinary gauge transformation, because the full metric is Schwarzschild. But if you restrict yourself to linearized order, then this is really a gauge transformation. And then whatever remained, so sorry, I should have said, so where h mu nu is 2gm by r u mu u nu. So this is just some algebra to manipulate and write it in this form. So the statement is that if you are looking at the linearized up to linearized order, means order in G. So up to a linear leading order in G, Schwarzschild metric is gauge equivalent to this eta plus 2h, where h has this form. Is this part clear? Okay, so that means that you can now ask, you can reverse this, and you can ask the following question: that is there a T mu nu such that, so I'm assuming all of you have seen linearized Einstein's equation in terms of what we call trace reversed metric. So is there a T mu nu such that is equal to, which source is this h? So just to set the convention, so here when I'm writing it like this, 8 pi g I'm setting to 1. C is always going to be 1 for us. And h bar mu nu, as you all know, is h mu nu minus. Sorry. So this is just for this example, I'm in 4 dimensions, as you. So this example is everything is in 4 dimensions. But it's just because of I want to illustrate the main idea. So minus 1/2. So the fact is that given this h and the corresponding h trace reversed h bar, can we find a u T mu nu which gives us this metric? Is this part clear? And you can see what will give, right? Because of the fact that if you took the T that we had written, so if you take this T to be, the integral d sigma. Now let me connect with what we wrote. So the stress tensor we had written was so I mean now 4 dimension just for this example. But if we are at just as we say for simplicity, we are looking at this case where u is the object is at rest. So if it is at rest, then of course this thing just rest is uniform velocity. So this thing just come out. So it is just going to give us p mu u nu, and then we have a integral d sigma delta 4 x minus x sigma. But this 1 sigma means one of the delta function you can integrate out, right? This is for delta function. So you can integrate the time delta function for sigma, and this object is simply then p mu u nu delta cube of x. If we choose the trajectory to be what we chose, which was just, sorry, I wrote it somewhere, I erased it, z mu tau to be mu tau. So no shift from some origin. Then you see that this is just equal to this. And now you see that clearly this structurally you can see why this h or h bar will exactly reproduce your t, because of the fact that D'Alembert acting on 1 by r is same as Laplacian acting on 1 by r, which gives us a delta function, right? Because dou t square acting on 1 by r is 0. So I'll give a delta function, that'll give us this delta function, and p mu, this m mu mu is just p mu, right? For momentum. So it exactly gives us that answer. So you see that this is showing us how, if you want to ask a question that if I'm looking at a Schwarzschild black hole from a large distance, that is I want to look at the linearized up to leading order in G, the metric of a Schwarzschild black hole, what is it sourced by? And it is sourced by the point particle of with this stress tensor. Is this part clear? Yes. Yeah. No. Everything up to here was absolutely full. What is the key statement where linearization went is here, because it is only to leading order. This is a pure gauge. Otherwise not. Otherwise the whole thing is there. So I drop this, and then I just look at this metric at to linearized order. I will just say quickly that this actually statement is remarkably true in Kerr black hole, as was shown by Justin Wine. So I will just write the result, but it's the same logic, but you have to do a lot more work to find these corresponding covectors and write it in some nice form. But I will give his paper reference where it's everything is explicit. So let me, can I erase this blackboard? Okay, go here. And so the statement that Justin Wines proved was, which actually then gave rise to a lot of new directions in classical and quantum gravity, is that if we, so I will just write the final result. If we consider Kerr metric, Kerr black hole, metric of the Kerr black hole, then it can also be written in this form. Where h mu nu, but it has a slightly now more complicated form, is and I will explain all the terms. So just bear with me for a second. Oh, that was this is here. Sorry. So as you can see, this is a two leading order in G that we are writing the metric. So it's the same logic, but it's absolutely remarkable result, and I will tell you why in a second. That you can write in this beautiful closed form where A is the spin of the Kerr black hole. I mean, I think it's called a ring radius, or the A is the spin parameter of the Kerr black hole that you see in the metric, and this dou is just dou by dou x mu. So this object is just A mu dou by dou x mu. And this may look weird, but of course, because sign starts in expansion at A dot partial, so there is no denominator actually. We just write it like that. So this is the form of this metric. If you take exact Kerr metric and you write it in this form, and then you say if I'm at order G, then this is a pure gauge and this is the metric. Now you can ask the same question: what is the T that sources this this metric? And this T is even more striking. Jan, is that more or less correct? And the T mu nu that sources this is a even more amazing form. So I will write it like this, and it is given by integral d sigma mu. Okay, I'm first going to write, then I will explain I'll explain the notation. Exponential where this is just this A star dou mu nu is epsilon mu alpha nu a rho rho alpha. So that's this compact notation. And so this exponential, of course, means you expand it. It's like matrix multiplication at every order. Say that again. Exponential of the spin parameter star with the partial derivative, where this star is defined like it's a matrix, it's a tensor which has two uncontracted indices. And so this exponential has this two uncontracted indices. So you do Taylor series expansion, and it's like a matrix expansion that that you do. Yeah. No, that's what I said. It's fake because because sine starts at a dot dou. So sine x is x minus x cubed by 3 factorial plus dot dot dot. So sine x by x is not has no 1 by x. Yeah. So you're right. But here, I'm just writing in covariant form, but we are in a stationary metric. So this everything is ai dou by dou xi. You're absolutely correct. I'm just writing it in the form that looks it's covariant. But this is a vector dot dou by dou x vector. Because it's acting anyone 1 by r. And just one last thing about this, because that will be interesting also. So you notice that this stress tensor, of course, has a remarkable structure. It has all these derivatives appearing, etc., etc. And if you do the oh, sorry about that. This is u. I apologize. This is u. And if you do the leading order expansion, then you notice what happens. So let's do up to one order in A. Then what will happen? So up to one order, first order in linear order in A. So this will become Kronecker delta. So that will just give us, I apologize, there is a m here. So then it will be d sigma m u mu u nu. That's the first term, which is exactly m u nu is p mu. So that's exactly the Schwarzschild, the one that gives us the Schwarzschild metric, right? It's the stress tensor of a point particle with no spin. But if you go to just the next term, then that you can check immediately that it looks like I will write it in a slightly. I will explain what I mean. So I'm going to introduce our sigma that I introduced before. So then you will see why the sigma I was calling spin now in a minute. So if you expand this, there will be some A, but in the end, the expression you will get is where the sigma you can immediately identify by this expansion, and you can check that sigma mu nu is nothing but epsilon mu nu alpha beta a alpha beta. So if you expand this to leading order, you put the star operator, and you just wherever you see this, you call it sigma, then you will see that you get this term. So that means that if you have a particle with what we are calling spin, that's why we are calling sigma spin. So if you have a particle with linear momentum or velocity u and some intrinsic spin sigma, then its stress tensor has this form. That point particle stress tensor has this form. I should not call it Kerr, I should call it order A, up to order A. What is absolutely remarkable about Kerr black hole is that, so in general, if a particle has other structure like neutron star, so it has higher order movements, then higher order terms in the derivatives will not be related to sigma or the mass. They will have new multiple moments. Yeah, just 1 second. But in the Kerr, everything is fixed by Neuer theorem, the mass and the spin. And so exact stress tensor of the Kerr black hole, which couples to its linearized metric, is this one. Okay. So I hope this convinces you why we objected objects like neutron stars or black holes as point particle, because at far distance, if you look at the metric, you can always source it by stress tensor of a point particle with multiple movements. Okay, and this is not an intuitive statement only, it's a very precise statement even for the Kerr black hole, as was shown by Justin. Yeah, sorry, there was a question. Yeah. 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 Exactly, because there are in all the infinitely many terms and they all have higher multiple moments, but in the case of curved black hole, they're all fixed by the spin. So that's the thing of Noether theorem, right? But if you now have a neutron star, it would have, instead of, you wouldn't have this closed form expansion because higher order multiple moments are independent of spin and mass. You understand? So I think it's a very good question. So I will just say one more line about it. So what this entire exercise is teaching us is the following: that if you give me any complicated object, and I want to look at its metric from a large distance, so I want to think of it as a point particle and ask what is sourcing this, what is the stress sense of the point particle, and then it has the following form for any object. And I think this is something Jan also, I think, indicated in his lecture. Okay, now I will transit to D dimension, because although I explained all this in 4 dimension, at least the Schwarzschild thing can be explicitly done in 4 dimension. I'm not sure if the curved black hole thing can be generalized to D dimension, but in any case, so let me just write the expansion to answer your question. So you see that I hope this examples tell you that if you give me any complicated object also, like a neutron star, but I want to view it from a large distance, then it's like a point particle with different multiple movements, and its stress tensor will have this form where this is the spin, this is some higher order multiple movement, and you can go on and on. In the car, everything is fixed by spin. That's the Noether theorem. That's the remarkable thing of Kerr. So I find this to be the most convincing proof of Noether theorem, honestly. I mean, in the sense of for Kerr black hole, because it's not very, you don't need to know Wald to know this proof. You just need to know linearized gravity. Okay. Any questions about this? Yes. Yeah. Well, not assume. I mean, at linearized order, it is a gauge, na? Yeah. No. So that's what we're saying. That is only telling us that if we view the Schwarzschild metric from a large distance, then what is sourcing that? What is the approximation of the point particle? Yes, absolutely. Yes. Only linear. No, I did not prove it. I mean, I don't remember the proof. I mean, the logic is same as Schwarzschild, but much more complicated. So you have to find appropriate coordinate to first write it in this form. And then once you have this form, then you examine what this object is, and he proves this is equal to this. So I will give you the reference. Yeah. There's a log also there. No, because I'm saying that this to linearized order, this becomes pure gauge. What you're saying is actually a very important point, because people who are experts in GR will identify this as what is called a log translation, asymptotic log translation. So what it is telling you is, you forget all this linearization, then the Schwarzschild metric can be written as this plus a transformation, which is not a gauge, but it's an asymptotic log translation. But up to linearized order, it's all pure gauge, so we forget. But it's not directly related to memory, because this is stationary solutions, so no radiation. Okay, any other questions? Ritesh, how much time? But is it for questions, or I can? Okay, so yeah, maybe I'll continue, but please stop me at any time. So now now that we have some understanding of why we are calling these objects with P and sigma, etc., let me start by giving the proof of the soft theorem. and I will complete it tomorrow. I don't think I will complete it today. So just let me quickly tell you what the only assumptions we made. So is there a question? So one was asymptotic freedom. Of classical trajectories. And the second is this objects as point particles replaced by astrophysical objects replaced by point particles. Because we are interested in radiation and not actually studying the objects themselves, so which means we are looking at them from large distance. And for the proof right now, we will only look at for any of these particles, incoming or outgoing, we will always so if you take a particle indexed by A, then its stress tensor we will write it as its proper time, which we will label by A. It's now, but the particle may not be uniform velocity, of course, so it has some acceleration. So okay, that's the for every incoming and outgoing objects, this is the stress tensor we are going to work with for now. Okay, no spin or anything, only this, only the linear momentum. And this assumption we can quantify. This assumption tells us that at late or early at late times, as mod sigma A goes to infinity, the trajectory is of the form is this clear? So this is the assumption one. Okay, the assumption that we are again and again saying, this is this part of this assumption, so that at late times it becomes a free trajectory because these terms just go away. Okay, so now we can just go back. Now we want to prove our soft theorem. So I'll just give you a rough sketch. I will start today and then we can complete it tomorrow. Yeah. No, we haven't used any equation. I will now come to the equation. They are any generally covariant equations. In the example we did, it's a linearized, yeah, exactly. There I did use linear sanctions equation. But just give me a minute, I will tell you why they are more general. Like I will explain. You are right, I agree with you. There I did use GR, explicitly use GR. Because we don't know if curved black hole is a solution of general random theory of gravity, right? Okay. So coming to Mukta Jyoti's question, which is relevant. So now we are going to, our objective, I hope is clear what our objective is. Our objective is to compute in small omega expansion, okay? And show that we get the result we wrote. But we of course start with Einstein equations of motion. Now, there's a nice fact that we can use, which is the following. Let us, so we have some generally covariant theory. The only assumption we make is that this theory should have Minkowski space as a solution. Okay, if it doesn't have Minkowski space as a solution, then that theory is not good for us. Okay, so any general covariant theory which has eta mu nu as a solution. So in particular, Einstein theory plus corrections, higher derivative corrections, for example, higher curvature corrections. Now, let G mu nu we write as eta mu nu plus, sorry, I will write 2 because of old habit, 2 H mu nu. But this H mu nu, when I write it like this, H mu nu is, I'm not assuming H mu nu to be linearized. I'm just assuming that my any metric, like we saw in those examples, can be expressed in this form. And this is true if the metric is almost Minkowski at large distance. So any metric which goes to Minkowski at large distance can always be written in this form. This doesn't mean, so this is important to remember, doesn't mean that is not a perturbation. It can be very large. But this way of writing the metric has a remarkable advantage that we can write the equations of motion as follows. So given this h, let me define. So there is some in this game now we have got a eta in the game, right? Like because it's just we just decompose it like this, exactly like in those examples, and then we can write. Of course, then I can define h bar mu nu, which is h mu nu minus. And because we have a background eta in the game, I can always choose my gauge fixing. I can fix my coordinates by choosing, so I can do gauge fixing, which is something I think most of you will be familiar with in linearized gravity, by these on their gauge. I can always use the same condition that we use, minus. Right? Again, it's important to remember this h is not necessarily a perturbation. We are just decomposing G in this form and choosing 4 gauge fixing conditions like this. And once you do this, then your equations of motion, it can be Einstein theory plus whatever. It has the following form. And that's the form we will use to prove our theorem. So we can show that exactly it becomes like linear gravity, but of course with one crucial difference, we don't really get an equation, we get an identity. So we can show that where box eta means box with respect to the fiducial metric is equal to mu nu, which is a function of whatever matter you will have. So I'll just put matter. And so what do I mean by this statement? It's not a really equation, it's just an identity. But how did we get it? All you do is to take your completed equation, whatever the nonlinear equation is, you just isolate this term, which is box h bar, and everything else you write in this side. Is this clear? So this will have, in particular, this will have mu nu matter plus terms which are second order in h. If you and you know really in because h bar satisfies the gauge fixing condition as this is 0, it implies that this T satisfies local conservation equation with respect to the fiducial metric, just by applying partial mu on both sides. This I should call it total. Right? So this is not an equation. I want you to remember this. It's just some identity. Okay, but this is the identity we will use to solve for the radiative field when you do the large X. Is a question? I think clear? Yeah. Yes. That's why we can choose any gauge. I mean, you know, right now we are, it's a good point actually, I shouldn't say it like that. So we are working with a gauge fixed formulation, but finally the answer we get, you can show that due to momentum and angular momentum conservation, it is gauge invariant. So the proof we are going to do is use a gauge, but the final answer we can then check its gauge invariant. Okay. Yeah, don't trust me. These are order 1 difference between your real lecturer and me. So, oh, yeah. Yes. I think so. Yes, I think so. Yes. Okay, I will say one more thing, then stop. We will continue tomorrow. So now, what we want to do is the following. So this identity we can now write in terms of the Green's function. And we are in classical theory, so we need to use retarded. Please ask if this part is not clear, retarded Green's function. But this is at any x, right? And what we want to do is two things. One, we want to first go to time domain because this is in, frequency domain, this is time domain. So we want to do two things. One, we want to do what we did earlier. And that we will call h tilde mu nu. And that will give us some integral integral dx0 and this t mu nu total. Now we are saying that basically we have a bunch of objects which are scattering, right? So this t mu nu total will be written in terms of the trajectory, but that I will do maybe tomorrow because I'm running out of time. And finally, we want to take the large, we want to evaluate the large mod x limit of this. So we want to write this guy. I mean, we will show that in the large mod x, this goes as what we wrote earlier. And then h tilde minus 1 mu omega x hat. I will not work out all the details because I will give you papers where it's worked out, but I will just tell you quickly what this object is if you take the large mod x limit, and we will start there tomorrow. So this is the equation we will start with. The large, sorry, I called it h tilde 0 earlier, no? H tilde 0. Some normalization. This is our entire space-time. Where k is the same k we derived earlier. So I will not bore you with the details of this equation. To go from this equation to this equation, you only have to do two things. Substitute the retarded Green's function and then take the large mod x limit. Okay, this retarded Green's function, in case some of you may have forgotten, it is simply, we can, the best way to write it is in momentum space. I'll just give you the expression. So you use this and then you do the, you have to do some little integral tricks. Now, but it's a similar thing that you must have done in Jackson also, if you remember. And then take the large, or if you have taken Logas class, then you take large mod x limit and you get this result. So this is we will start here because this is a very compact form. You see, it's still not an equation, it's an identity because this depends on h, but it looks very manageable. Right. So now what we want to do is take the small omega expansion and see what contributes. Right. So far, it's all very dependent on the theory, the stress tensor, everything, right? So far we haven't solved anything, but we will see what happens when we take the soft limit. Maybe I can stop here and we continue from here.
We have a few minutes for questions.
Yeah.
The fact that the black holes behave like point particles moving along world lines.
When viewed from a large distance, yeah.
This depending on the fact that we did an Einstein theory, because otherwise by T mu nu, which one was sourcing h bar mu nu, will also contain order h squared terms.
But then first we have to show that those black hole solutions exist in the theory you have, right? I mean, I don't know. Yeah, I mean, so that entire thing depends on the existence of the solution, of course. Yeah. I don't know if we cannot prove. If you give me a theory which has a black hole solution, then probably one could do it. But of course, what we did was in GR because use the fact that it is a solution in GR.